Okay, so yeah, once again, I, I, I would like to start by thanking the organizers, Professor Nimai, Professor Dilip, Professor Subhakanta, Professor Kesarjit, Professor Robertson, and all members of the organizing committee for their efforts in organizing this workshop to celebrate the International Year of Quantum Science and Technology. And I would also like to thank you for inviting me to share some of my thoughts and perspective on the topic of quantum computing. So the original title of my talk that I sent to Professor Nimai was Quantum Computing, Where Are We Going? However, while I was making the presentation, it became clear to me that I don't actually know where we are going. So I have made some modification to the title of my talk, which is now Quantum Computing, Where Are We Now? So I hope that's fair. So as the title suggests, this is not going to be a technical talk, but rather an overview of the current status and progress in the field of quantum computing. And yeah, so what you see on the cover slide is a picture of the famous quantum computer by Google, designed by Google using superconducting circuits. We will talk more about this later. So this is the outline of my talk. I will start with a brief recap of quantum revolution. The quantum revolution that took place in the 20th century and what's happening right now. Then we will discuss a bit about, briefly about what quantum computers are, the different types of quantum computers. And then we will go to some possible applications of quantum computers, what they're currently being used for, what uses these machines have. Then I will talk to you about something called quantum advantage and the quest for quantum advantage and why people are trying to solve quantum advantage these days. And then we will conclude with some remarks and discussions. And yeah, if you have any questions in between, please feel free to interrupt. So the first quantum revolution, it occurred in the early 20th century, right? This was back when people were trying to understand phenomena like black body radiation, where the spectrum of the electromagnetic radiation emitted by black bodies could not be explained using classical mechanics, for example, or the photoelectric effect, right, where you shine light on materials and it emits electrons. However, how and under exactly what kind of circumstances do you emit these electrons? It could not be explained using the existing classical theory. So all this phenomenon led people into thinking that light actually consists of particles, right? But then if you think about light as particles or electrons, and when you put it in a double slit experiment, right, like the famous Young's double slit experiment, then you observe things like interference patterns and so on. So this led people to believe into what we call the wave particle duality of light, right? So like light behaves both as a particle and wave and so on. So these are some of the theoretical ideas leading to the development of quantum mechanics. And many people, like Max Planck, Albert Einstein, de Broglie, there were so many people who were responsible, who played very important roles into the development of quantum mechanics. So the first quantum revolution used these ideas to understand nature and reality. So these were theoretical ideas, that were used to develop quantum mechanics. And then using these ideas, you try to understand nature and reality, with all this kind of experiments. Yeah, but it wasn't just Einstein or de Broglie, many people contributed to the development of quantum mechanics, or the first quantum revolution, as we call it. We can summarize it. You can find a nice picture, so the picture that I would like to show is the famous Solvay conference of 1927. So this is when most of the pioneers of the quantum revolution met for this conference. So for those of you who are not aware, the Solvay conference is one of the most prestigious conferences in physics. It's held every 3 years. And this is a conference, you can't just go and attend this conference. You have to be invited. And amongst all the Solvay conference, the 5th Solvay conference of 1927 is considered to be the most important Solvay conference. So as you can see from the picture, many important people like Albert Einstein, Max Planck, de Broglie, Heisenberg, Schrodinger, Langevin, they were all present together in this meeting and this is when like quantum mechanics was sort of, you can think of it as when quantum mechanics was developed in this conference. The importance of this Solvay conference of 1927 is highlighted by the fact that 17 of the 29 attendees of the conference won the Nobel Prize. So this is why like the fifth Solvay conference of 1927 is considered to be the most important meeting of such kind. And this is when all the pioneers of the first quantum revolution met. Okay, so that's about the first quantum revolution. So in the words of American scientists, J.P. Dowling and Australian scientist G.J. Milburn, they said first quantum revolution gave us new rules that govern physical realities, while the second quantum revolution takes these rules and use them to develop new technology. So the first quantum revolution was all about theoretical ideas and formulation of these ideas, using these ideas to understand nature. The second quantum revolution now takes these ideas, takes this rule, and we use them to develop new technology. That's what the second quantum revolution is all about. And the second quantum revolution is happening right now. What led to the development of second quantum revolution? So after the first quantum revolution, after so many years, what led to the development of second quantum revolution? So one of the reasons is of the second quantum revolution is driven by experimental and technological breakthroughs in isolating and controlling individual quantum objects, which we will later call qubits. For example, the Nobel Prize in 2012 was awarded to Serge Haroche and David Wineland for their technological and experimental methods that enabled measuring and manipulation of individual quantum systems. So these guys could, control and manipulate individual photons using sophisticated optical devices. They could also use photons to capture ions and atoms and things like that. So it was for the first time that, these guys had perfected the experimental setup to isolate individual quantum object from its environment without destroying their quantum mechanical properties, which was not possible earlier. So once you manage to isolate and control and manipulate individual quantum objects, then you can really start taking the next step forward in understanding what these properties do. Now, after 10 years, the Nobel Prize in Physics was again awarded to Alan Aspect, John Clauser, and Anton Jellinger. So these guys won the Nobel Prize for, you can think of it as sort of an experimental verification of quantum entanglement. So Albert Einstein was not convinced about quantum entanglement, although ironically it was his, understanding of all this photoelectric effect and things that led to development. He was not convinced about quantum entanglement, and he called it spooky action at a distance. In order to disprove Albert Einstein, John Bell, he formulated something known as Bell inequality, which, when violated, would prove that quantum entanglement is real and that quantum mechanics is correct. However, it remained a theoretical concept until, people like Alan Aspect and John Clauser demonstrated it experimentally that, Bell inequality is violated. And then Anton Jellinger, did a lot of works on quantum teleportation, which is based on quantum entanglement. So these guys, like the winners of Nobel Prize Physics in 2022, sort of proved quantum entanglement is real. So, driven by all these breakthroughs, experimental breakthroughs in, controlling and manipulating individual qubits, proving quantum entanglement, it led to second quantum revolution, because we can now say that the technology is now maturing enough to do some real things, some real applications with quantum mechanics, and not just theoretical ideas. So so unlike the first one, in the first quantum revolution, all these developments and theoretical ideas that took place in national labs, research institutes, universities. However, in the second quantum revolution, private industries and corporations are now taking a big lead. Companies like big corporations like IBM, Google, Microsoft, Amazon, they're investing a lot of effort, a lot of money into developing quantum technology. So this is something, which obviously, because in the first quantum revolution, there were only theoretical ideas, you could not do it. And now like private players have come into the front to take the second quantum revolution forward. However, it's not just the private players, but also governments all over the world. They have invested, or at least make plans to invest a huge sums of money investment into quantum technology, including like the government of India announcing $1 billion for investment in quantum technology. Now, this is a data that I took in 2022, and yeah, there has been a lot more investment and effort all over the countries into like quantum technology. But why? Why are people spending, investing so much amount of money? Suddenly, why are people making so much effort into this quantum technology? In order to understand this, we have to first, like try to understand what are quantum computers and what are the different types of quantum computers. So yeah, I think you already heard a lot of talks on quantum computers, and so, but we'll just like quickly go through a few slides on quantum computers and what are the different kinds of quantum computers for the sake of completeness. So quantum computers, these are like devices, that exploits the properties of quantum mechanics, properties of quantum mechanics like superposition, quantum entanglement, this kind of things. And the basic building block of a quantum computer are what we call quantum bits or qubits. So in order to understand qubits, one can think of classical bits, right? Classical bits, they are basic units of information. A bit can take two states, 0 or 1, plus or minus, on or off, the switch, things like that. So a qubit is similar in the sense that a qubit can take two states, 0 or 1. However, it can also be a combination of 0 and 1, which is a property called superposition. And the most popular representation of a qubit is what we call the Bloch sphere. And the two poles of the Bloch sphere represent the two states, 0 and 1. And any other point on the sphere represents like a superposition of the two states, which is not possible for classical bits. So this is a very nice geometrical representation of a qubit. And then, like this is how a quantum bit or a wave function can be written in terms of, the superposition where the coefficients represents the probabilities of the state being present in either 0 or 1, okay? So unlike the classical bits, in the quantum bits or qubits, we use the direct notation to represent the 0 or 1. Now, this is just like a mathematical definition of qubits. And so when we want to understand what are the different types of quantum computers, we have to understand the fact that this is a mathematical definition, and there are many ways that one can realize a qubit, okay? So you need a two-level system that satisfies the properties of quantum mechanics in order to build a qubit. And a qubit can be built in more than one way. And this is what leads to the different types of quantum computers. Different qubits, different design of qubits leads to different types of quantum computers. So yeah, so there are different types of quantum computers. So we'll start with the example of the picture that I showed, which is what we call, it's like the most popular quantum computer available is what we call is the superconducting quantum computer, okay? In a superconducting quantum computer, the qubits are made using tiny circuits made of superconductors, usually like a Josephson junction or something like that. So unlike other quantum computers, the qubits are built using artificial two-level system. So like in other quantum computers, you have like a ion or a neutral atom, that can take two states, which is naturally occurring. However, in this case, it's an artificial like two-level system. So it's a superconducting circuit. Now, this type of quantum computer is very popular in the sense that the biggest player in the industry, like Google Quantum or IBM, have adopted this superconducting circuit model for building their quantum computers. Now, besides Google and IBM, there are other companies, that relies on the principle of superconducting circuits for quantum computers like Rigetti, IQM, and so on. Then there is also photonic quantum computers, which uses photons, light to carry and process information. So usually you have some kind of generator of photons, that acts as a quantum light source, and then these photons carry the information, and then you have logical gates in between, and then you have like single phone detectors in the end of your circuit, which serve as some sort of measurement. Okay, and this is like another popular quantum computer that uses photons to build the qubits. And companies like PsiQuantum, Xanadu, or Gar Computing, they use photonic quantum computers. And then there is neutral atom quantum computer. Here, neutral atoms that are neither positively or negatively charged, they are suspended in ultra high vacuum using optical tweezers. Okay, and using lasers and optical tweezers, you can manipulate and control and rearrange all these qubits and atoms. Okay, and then many companies like PASQAL, Quera, Atom Computing, they rely on neutral atom quantum computer. And I work in like one of these companies. So we build quantum computers using neutral atoms, and then we try to find applications of this computer. Then there is also trap ions. So instead of using neutral atoms, you use ions, that are positively or negatively charged, and then these ions are trapped and manipulated using electric and magnetic fields to store and process quantum information. And then like many companies like Quantinuum, IonQ, Alpine Quantum Technology, they use trap ion. This is another popular type of quantum computer that people are developing. So in this talk, I'm not here to compare which quantum computer is better than, like which. I think like every type of quantum computer, will have some advantage, like with respect to certain tasks. This is not the purpose of my talk. I just wanted to give you a brief overview of the existing technologies and the different types of quantum computer. Recently, a few days ago, Microsoft unveiled a new type of quantum computer based on Majorana qubits. Okay, so as I was mentioning previously, the second quantum revolution is happening right now, which means that right now people are working on something extraordinary towards building quantum computer. And this is like proven by the fact that just a few days ago, Microsoft unveiled its Majorana quantum computer made using topological qubit. Now it's too early to say, people are commenting a lot on, the claims of the Microsoft, whether this is truly topological or not. But this is quite an achievement from Microsoft, and we have to see. Yeah, so all these quantum computers, what are they going to be used for? Like, what are the potential applications of these quantum computers? We don't know for sure yet, in the sense that sometimes you build a technology and then afterwards you find the applications of such technology. Okay, so it's not like we don't know for sure yet that this will be all the potential applications of quantum computer. However, some of the applications that people are working on for applying quantum computers, I will briefly mention. The first is quantum simulation and material science. Yeah. So the idea is that you use quantum computers to mimic and model complex quantum systems, which are too difficult to be studied using classical computers. Okay. So like quantum many-body system, non-equilibrium dynamics, this kind of things, yeah, like complex systems that you cannot study using classical computers. So if we use quantum computers, this could be helpful in solving long-standing physics problems that remains very difficult until now. And then this could lead to the discovery of novel phenomena and phases of matter, which are not yet possible to be explored using conventional computers. So like quantum simulation, material science, discovery of new materials, this is one of the most promising applications of quantum computers. Besides this, people are also working on using quantum computers for quantum chemistry, using quantum computers to do molecular simulation, which can in turn lead to discovery of new drugs, which cannot be studied using the existing computational resources. And then there is also quantum optimization, where you minimize a certain loss function using a quantum computer related to tasks like logistics, finance, combinatorial optimization, this kind of things. These are like very, very hard tasks using classical computers, but using quantum computers, the hope is that you can have some sort of advantage. Then there are also potential applications in quantum machine learning, where you use a quantum computer to perform certain machine learning tasks, like training data, for generative modeling, this kind of things. We know that, training data for generative models like ChatGPT and so on, this takes up a huge amount of computational resources. So maybe, quantum computers can be used to, do some of these machine learning tasks. So this is like one of the applications. Or you could use the results from quantum computer, the outputs from quantum computer, to do some classical machine learning, which can then be used to understand new phases of matter. I will not go into the details of this because I am not an expert on these fields, but I think like the next two speakers, based on the schedule, the itinerary I saw, I think the next two speakers will probably go a bit deeper into quantum chemistry and quantum machine learning, so I leave it to them. Another area, where quantum computer has like promising application is quantum cryptography, where you encode data using a quantum computer, and then you can show that it is possible to break such encryption using a classical computer. Or you could break existing public cryptography using quantum computers. An example is source algorithm, because many of this, we will discuss a bit about source algorithm later, but many of this public encryption are based on factorization of, prime factorization, finding prime numbers of integers. And then you can show that using source algorithm, this can be done exponentially faster than a classical computer, which means that existing encryption technology are vulnerable to quantum computers. Yeah, so these are some potential applications of quantum computers. So in all these applications, what is the current goal? What are people trying to do? This is something that I will discuss now. So in all these applications, people are trying to achieve something called quantum advantage. Some people call it quantum supremacy. Some people call it quantum utility. Some people call it quantum advantage, but it's the same thing. So the idea is there a task where quantum computers can outperform classical computers? This is like the most important question for now. Is there a task where quantum computers can outperform classical computers? And I underline outperform because outperform could mean in terms of accuracy, it could mean in terms of efficiency, it could mean in terms of energy efficiency of, like running these computers. If you can find an advantage, if you can find a task where quantum computers can beat classical computers, with respect to any of this, then you can say you have a quantum advantage. So this is like something that people are trying to achieve at the moment. And when we talk about quantum advantage, there are two categories of problems. The first type of problem is tasks where you can prove mathematically that quantum algorithms have some advantage over classical algorithms. So you have like a mathematical proof. You can there is a proof available that quantum algorithms can beat classical algorithm with respect to certain tasks. An example is the Grover search algorithm. So the Grover search algorithm is, it's about searching an item in an unstructured data list. Okay, that's what the Grover search algorithm is. You want to search for an item in an unstructured data list. So Consider you have 10 balls, and these balls are numbered from 1 to 10, okay? And then you put all these balls together inside a box. And the task is to find one of the balls, say a ball number 3, okay? So how long will it take to find such an item from an unstructured data list? I call it unstructured because the balls are not arranged according to any structure, like ascending or descending order. So it's unstructured. So how long will it take? What is the complexity of such a problem? In the best case scenario, in order to find like this particular ball that you have in mind, maybe you put your hand inside a box and then you pick up a ball. And if you are lucky, the first ball turns out to be the ball that you want to find. Okay, so you only needed like one query. However, in the worst case scenario, you will have to pick up all the balls one by one until you find a ball in the end. So you will have to make 10 such queries. So in an average case, you would require like n by 2 queries in order to find the marked item in your unstructured data list. So the complexity of such an algorithm, okay, is polynomial in time. However, any classical algorithm, the complexity will be polynomial in time because it scales as n. However, if you use Grover's search algorithm, a quantum algorithm, then you can show mathematically that it can be performed in the square root of n time, which means that there will be a quadratic speed up of solving the problem. So that's the Grover search algorithm. Another example is the source factoring algorithm. So the idea is, given an integer, you want to find the prime factors. Now, for a large integer, this is a very, very difficult problem. And in fact, this is the basis of many of the public encryption. So this is known to be a very hard problem. However, if you use source factoring algorithm, a quantum algorithm, then you can prove mathematically that you can have an exponential speedup over the classical algorithm. So there are other algorithms that provides guarantees of such advantage mathematically. Okay, so however, the problem with this type of the issue with this type of problems is that in order to actually see this exponential or quadratic speed up with quantum computers, you need many, many qubits. You need millions of qubits, and your quantum computer has to be perfect. There cannot be any noise. Okay, so you cannot have any noise in your quantum computer, and you have to have like number of qubits, which is not possible at the moment. So a million qubit noiseless quantum computer is far from the horizon at the moment. We are in the era of noisy intermediate scale quantum computer, next era as we call it. And therefore, using these intermediate scale noisy quantum computers, it is impossible to achieve quantum advantage in this type of problems. Okay, so there is no way we can achieve quantum advantage. However, there are other tasks which we can try to find where there are no such guarantees mathematically that you will have an advantage, but nonetheless that are known to be computationally challenging for classical algorithms. And I will discuss like briefly about some of these tasks and the claims for quantum advantage into some of these tasks. So I think one of the first claim of quantum advantage was made by Google with their Sycamore processor. This was a paper back in 2019. They used their superconducting processor and they claim quantum supremacy. They claim that their quantum computer can beat any classical computer in 2019. So the task they had was some sort of like random circuit sampling. However, after 5 years, a group of Chinese scientists refuted their claim that what the quantum computer of Google can do can be done much more efficiently using classical computers using GPUs. So it took them 5 years. So the claim of Google claiming quantum supremacy was destroyed in 5 years by this group of scientists. Then more recently, in 2023, IBM, they made another claim for quantum utility or quantum advantage using their 127 qubit Eagle processor. The task was some quench dynamics of Ising model in some heavy hexagon lattice that is, reflected in the geometry of their IBM quantum processor. However, the interesting thing was that when we saw this paper, this claim, this Nature paper by IBM, some of us, like I was in Berlin at the time doing my postdoc, and then we were looking at this paper, and then we discussed, and then we discussed, and then we said there is no way this is going to be a quantum advantage, because what they have done looks like quite an easy task using classical computers. So we were discussing about this and how they can make a claim of quantum advantage using such attacks. And then, like within a few months, the claim of IBM got destroyed by several groups. So the thing that they could do using their quantum computer, a classical computer or laptop could do it in a few seconds. So, and within a few months, like many papers using different kinds of techniques, they disproved the claim, they refuted the claim of quantum advantage by IBM. More recently, again, last year, D-Wave, another big company using quantum annealing processor, made claim on computational supremacy in quantum simulation. Again, like the work they do is related to quench dynamics, like non-equilibrium physics. And this is like only 1 year old. And yeah, and so they use a lot of classical techniques, tensor network techniques, neural quantum states to compare the performance of their D-Wave quantum computer. And then they said that there is no way classical computers or classical techniques can do better than their quantum computer. Yeah, we have, I read this paper like quite in detail myself, and I think the results present look very solid. However, it will take time. If somebody wants to counter check their claim, it's going to take time. People need to run this test and then see what they're claiming is actually true, or if there can be better classical algorithms that can beat these claims of quantum supremacy. So yeah, this claim is unrefuted so far because it's only a year old. And then also, like even more recently, there was another claim by Google. Although their claim got refuted in 2019, they made another claim after 5 years of quantum advantage using their latest Willow processor. And the claim they make is quite interesting. So they say that Willow's performance on this benchmark is astonishing because it performed a computation in under 5 minutes that would take one of today's fastest supercomputers 10 to the 25 or 10 septillion years. So like a classical computer, the best classical computer could take 10 to the power 25 years, but their quantum computer can perform this task in under 5 minutes. Well, the claim, if it holds, is like truly mind-blowing. However, we have to see. We have to wait, and then people need to check their claims, and maybe their claim is true and they can establish quantum advantage. Maybe people again refute their claims. So we have to wait. Yeah. So yeah, so far, because it's just so recent, the claim has been unrefuted. Yeah, so yeah, these are some of the claims, and I would slowly like to get into the discussion mode, about what these claims mean and what it means for the technology and for the field. So first of all, again, I believe that it is unclear how long the quantum advantage claims will hold, and we have to wait. We have to wait whether they get refuted or whether there is truly a quantum advantage. But also, even if the claims are found to be true, even if there truly is a quantum advantage in all these claims that was made, these problems so far do not have any real world applications. So these are mostly, non-equilibrium dynamics of some specific model or random circuit sampling, like very, very particular scientific and academic tags that do not seem to hold any real world value at the moment. So even if the claims are true, they don't have any real world applications. So practically useful quantum computing is not here yet. This is what I would like to say. Well, this is like the current status, that practically useful quantum computing is not here yet. And quantum computing's ChatGPT moment has not arrived. Where, in AI, everybody start using ChatGPT and, it starts making impact in their life. That is not the case with quantum computing. So we are not there yet. Many industry leaders, have weighed in their opinion, including NVIDIA CEO Jensen Huang, who suggested that useful quantum computing will take 10 to 15 years. However, there are other like industry leaders like Microsoft founder Bill Gates who, bet this timeline to 3 to 5 years. Now you may wonder, why do we care about the opinion of these, leaders or these billionaires? It matters because we are in the second quantum revolution, led by industry. And when NVIDIA CEO Jensen Huang predicted 10 to 15 years for useful quantum computer, the stock market crashed. The quantum computing stock market crashed, like companies lost millions of euros. And so what I'm trying to say is that public opinion, like opinions of these leaders do play a role into, like how we can accelerate, this revolution in the second quantum revolution. Yeah, and I think this is going to be my last slide. And when it comes to useful quantum computing, I think at the end of the day, people will continue to debate whether, there really is hope in useful quantum computing, or whether it is just hype. People are just like making up stories, and maybe, it will not be useful at all. So people will continue to debate on this. I personally, as somebody, who is trying to be deeply involved, I am very hopeful. I think we are heading in the right trajectory. I think there will continue to be claims on quantum advantage, and many of these claims will be refuted. And I think that's not a bad thing, right? And I think this is the beauty of science, At the end of the day, whether it's quantum or classical, I think we are making huge progress. But we have to be careful, though. As a scientist, we have to be careful while talking about the capabilities of quantum computers. We should not make unrealistic claims, or contribute to the myths surrounding quantum computers, because this will lead to the public losing trust in science. As a scientist, I think we have to be as scientifically accurate as possible, acknowledging the current limitations and capabilities of the technology, while continuing to remain hopeful about useful quantum computers. So yeah, with this, I would like to thank you all for your attention. And yeah, that's it from me. Thank you very much.
Thank you, Dr. Augustine. Now we have some time for questions and answers. Mike.
Hi, Augustine.
Hello, Oza.
So I have a very simple question. I heard that in the recent times, this neutral atom candidate has become quite promising in terms of the recent development. So what are your comments on that? And what is the specific advantage that it offers compared to the others? Can you elaborate a little bit on that?
Yes, I can comment a bit on that, also especially because I am working with the neutral quantum computers. So one of the advantages of neutral atom quantum computer is the flexibility in the geometry. So we are not like constrained to any kind of geometry. So we can have like a qubits in a 2D lattice or 3D lattice, or in some complicated like geometry where you could possibly have more applications. So this is one of the advantages. And the other advantages, like I think there are also like more experimental advantages, like you do not need such a low temperature in order to maintain this neutral atom and so on. So yeah, so I would say the flexibility in the geometry is the main advantage. Yeah.
Okay, then I have one more. Okay, so in the context of this quantum supremacy, this was demonstrated using Google's quantum computer, which, if I remember correctly, in 2019, it had 53 qubits. Now, what is the status? And in terms of the actual use of the quantum computers, there is this need for error correction. So how will it be in the case of the neutral atom system?
Yeah, that's a very, very excellent question, Oda. So for the recent claim, the 2024 claim by Google, this is like they claim that they have a method to control the error. So with the increasing number of qubits, their error, they could keep their error under control. And this is what led to their quantum supremacy claim. I think when it comes to neutral atom, or at least, like the things that I'm familiar with, we are not focusing too much on an error-free quantum computer at the moment, but we are trying to ask questions like what can be achieved using, this noisy quantum computer. So in an analog setting. Yeah. So many people believe that even using this currently noisy quantum computers, you can have some sort of advantage. And that's like the current focus.
Yes. Yes, when as a layman, when we read increasing number of qubit and Chinese people have attained this much qubit, like that we read. And why when we increase the number of qubits again, more and more, why the power of the quantum computer is increased, and this number is not limited, or it may go to infinity. So what is your comment on this? We cannot understand fully about it.
Yes, so the idea is that, so we have to think about like quantum advantage again here. If we have limited qubits, if we have, let's say 5 qubits or 10 qubits, we can easily simulate 5 qubits using our laptop. Okay, so there is no advantage using a quantum computer for 5 qubits or 10 qubits or even 20 qubits. We can easily simulate a 20 qubit system using classical computers. So there is no point in having a quantum computer. You will not have any advantage. You will not see anything that you do not see. However, when you extend beyond this like scale of 30 to 40 qubits, you start seeing other phenomena like quantum many-body effects, like quantum many-body effects you start seeing when you have large system sizes or qubits, that are very, very large. And it is also in this regime that our current supercomputers, classical computers, we cannot understand like a 50 qubit system or a 100 qubit system. We don't know like how a system comprising of 50 qubits will behave because we simply do not have the computational capacity. So if we have a quantum computer with like 100 qubits, then we are in the quantum advantage regime. So yeah, so the more the qubits we have, the better the chances of quantum advantage and the more things that we can explore.
Hi, Augustine. I just have a small this thing. Like, when you were talking about photonic quantum computers, maybe it's because not that very technical talk. It's actually Q modes, right? Because they work in the Fock space.
Yeah. Yeah, I'm like not, I don't know much about it, so I just like mention it to give an overview.
Because I'm talking about it in my talk a bit. That's why. Yeah, it's fine.
Okay. Yeah. So yeah, I think you are the right person to take over. Yeah. Thank you.
Any other questions? Comments?
Next question, call. So, okay, we understand about quantum computer. But people are talking about teleportation and all that. Is it feasible, or I don't know, like Germany people have succeeded something we read in the newspaper. But we understand quantum computer to some extent because it has a qubit and there is superposition and all that. But this teleportation and all that, what do you feel about it?
So yeah, I think there has been experimental demonstration of quantum teleportation. So I think that's like the kind of things that Anton Jellinger was working on. So I'm not like 100% sure what would be the, like a context when it comes to using quantum computer for teleportation. Maybe like, yeah, I don't know, like in, quantum key distribution, quantum communication, they might be useful. Yeah, so yeah, I think they might be useful when it comes to quantum communication, like distributing like all these keys and so on. There was also experiments, like by a group in China using, they fired 2 photons using a satellite and, they saw some teleportation experiment. So I think, again, these are like like I would see more challenging things. Yeah. I mean, I have not seen like claims of quantum advantage or, this kind of things when it comes to teleportation. Yeah.
Okay. If there are no further questions, then let us thank Dr. Augustine once again. Thank you, Dr. Augustine.
Thank you so much. And yeah.